So my name is Matt Berger, and I run the Eagle team at Autodesk, amongst other teams. So I'm also responsible for Tinkercad, was responsible for 123D, and a variety of other products, mostly related to sort of the consumer and the sorts of things that are really intended to kind of drive the Autodesk role in the maker, hacker, emerging market, startup communities moving forward, okay? This is who I am. If you need contact information, if you want to look at any of my open source hardware projects, any of those things, I used to run product at SupplyFrame, which is a company that owns Hackaday. So if any of you are Hackaday readers or avid Hackaday readers, follow Hackaday projects or anything like that, you'll see me in the comment threads. You'll see me on the chat all the time. Obviously not during work hours, because that would not be a good thing. I self-identify really as an electrical engineer. My background is really related to radios. I love to build radios and RF stuff, wireless stuff. I love materials problems. I love physics problems. My education is in applied physics. I really like physics problems. I also do a lot of teaching, a lot of mentoring, really trying to build opportunity through technology and enabling people to build stuff that they just couldn't build before. If you are interested and you think that what we talk about today is interesting, you happen to be in the Bay Area, if you're down in LA, I'm going out to New York just after the holidays. I do a lot of stuff on the road where I do a lot of workshops that are generally free to the public, things that I do out of my own pocket, just as a way of trying to contribute as much as I can to people's understanding and education and how they can transform things through science. So a lot of interesting things that I build. Some things, robotics, and I started doing model rockets at a very early age. I won't sort of belabor too much about this kind of stuff. That's a Hackaday logo up in the upper right-hand side over there, which I love, which is that skull and wrenches. Sorry if that looks ominous. I promise it isn't at all indicative of anything that you should be afraid of in this class. Let's just level set first, though, before we get started. I want to be absolutely upfront with you. This was my desk before I left and came here. And I want to stress that because I think it's one of those things which is lost in a discussion about coming up to speed on how to build things with electronics. The fact that, hey, there's somehow this perfect workflow and everybody follows this perfect pattern and it's predictable and everything looks very clean. Look, all of that stuff which is connected together, there's an FPGA board down there, there's an Arduino there, there's a breadboard, some stuff that I did on a breakout board. That's very real. I'm testing an SPI multiplexer that allows the Arduino to program an FPGA using wireless connection up to the cloud. So this is real. It's sitting on my desk right now. It is a big mess of wires, and it's ugly, and it's nappy, and everything about it is probably not terribly flattering, not reflective of, or not a reflection of my best engineering skills. But the point is that I get the job done. And at the end of the day, I want to stress what this really represents. All we do when we build electronics, when we build printed circuit boards, is connect components together in interesting ways. Unlike mechanical engineering, which has a different problem. Mechanical engineering has the problem of you may be creating a part which has never existed before. In the electronics space, almost invariably, with very few exceptions, we buy 100% of the components that we use on our circuit boards. So we go to a third-party company that's a distributor for some larger manufacturer. We buy a part which is purpose-built for some specific function or some set of functions. And so in this case, all I'm doing is connecting components together in interesting ways. If you sort of rewind all the way back to your 5th grade electronics class or your 5th grade science class, it's probably just general science at that point, I don't think you had an electronics class, but that battery light bulb switch concept, that's all we're doing. We're just doing it at scale, and we're scaling it up. And the interesting thing is that more and more, we're moving towards a platform approach to electronics. So it used to be that 10 years ago, when Arduino came out, I would look at the Arduino and say, oh, well, it's great, but, don't you know that I retired my old spring-loaded Elenco electronics kits 25 years ago, and I'm not touching those. But the truth is that it's super convenient. It's super convenient, and it's a software platform that allows somebody who is a non-engineer, non-physicist, non-materials person to interact with the real world. And that is what makes those things so relevant. So Arduino, Raspberry Pi, BeagleBone, Gumsticks, you name it. You can go out and find all manner of companies that are building these platforms that allow you to write software that can control the real world. So if I'm a mechanical engineer, I'm an industrial designer, I'm an artist, I'm a maker, I'm a hacker, I'm a this, I'm a that, I no longer have to have all of the requisite information required for me to go out and start to engage and start to build things. Instead, I can use somebody else's platform which provides me a gateway without having to know all the low-level details. So me, as a 25-year electrical engineer, paid electrical engineer, and somebody who's got a background building ECAD software, this is on my desk today. My prototyping platform is an Arduino and a breadboard. And it looks a lot like what my dresser looked like when I was 13 years old. Again, not terribly flattering, probably didn't do a lot for my social life, but definitely important. So in the ECAD world, in the electronics design world, when we build a printed circuit board, there's sort of two views of the world. There's a symbolic representation of the world, and then there's a physical representation of the world. And if you extrapolate that even one step further, there's a physical representation of that with geometry, with three-dimensional spatial geometry. In the symbolic representation, we call this a schematic, okay? And the schematic uses symbols to describe a circuit. So on the left-hand side, even though it kind of doesn't look like it, maybe it does a little bit, that's a mini USB connector there. Over here, those are capacitors. And a capacitor, if I described it in engineering or physics terms, I would say, well, it's two metal plates separated by a dielectric. Well, that kind of looks like two plates of something separated by some gap in between it. The dielectric is basically just something which is an insulator. It's a fancy way for us to say insulator. Okay. You'll notice more and more things like a fuse up here, which kind of has that same curly thing that if you look inside of a fuse, it has that same sort of curl to it. Resistors are typically a squiggly line. The reason is because as the length of a piece of wire gets longer, the resistance increases. So we draw something which is symbolic, which represents exactly what that thing is, exactly what it does, as best we can. Now there's some things which are just ambiguous. Some things which are integrated circuits, where there's multiple functions or there are complex functions inside of those things. And for those sorts of things, we end up using something like a rectangle up here. So we'll use a rectangle, we'll add some pins to it. And what those pins are is analogous to the contacts on a circuit board where the components will make contact with the surface of the board. So a printed circuit board, its physical representation would look something like this. In the physical representation, what we've done is we've said, okay, that USB connector, this looks maybe a little more like a USB connector, not much, but that USB connector over here has a series of small metal pins hanging off of the back of it. If you've ever looked at a circuit board, you'll see the pins on there. Those pins are where the electrical connections are made between that connector and whatever cable gets plugged into it, and then the rest of the circuit itself. So connected to that, on multiple layers on the board, the red represents one layer, the blue represents the opposite side of the board. So I've got a top side of a board and a bottom side of the board. Now boards can be multiple layers. We'll talk about that in a second. But in the case of this, the red represents the top side. And the way that we build a circuit board is similar to the way that we do other photolithographic processes like printing. So we start with a board which is pre-clad. What that means is it's a sheet of fiberglass with a thin layer of copper already spread over the top of it. We apply a mask. And the mask is to protect whatever copper we want to leave behind. We drop it into a material called into a solution called an etchant. And what the etchant does is it removes all of the copper that we don't want on the board itself. So if you imagine a solid sheet of copper, we remove the things that we don't want. It's a standard photolithographic process, very similar to how we do things like offset lithography for printing. Okay? So these little red lines, those represent the connections that I want to maintain between those components. There'll actually be a thin foil of copper on the board, something like 1.62 mils thick. Okay? 1.4 mils thick, sorry. So those thin foil lines are everything that you saw in those wires now represented across a two-dimensional plane. So that's how we connect components together in interesting ways in a contemporary sense. Now the cost to build a circuit board is relatively inexpensive. To get the bare board fabricated is relatively inexpensive. But what does relatively inexpensive mean? Meaning for $7 a square inch, I can get a circuit board made that has copper foil on one side and copper foil on the other side. I send off my artwork files, which are the things that I get out of the CAD software. And when I submit them to somebody, they send me back a circuit board 7 days later, which looks totally pro. Okay? So it's relatively inexpensive to get into it. It's great because it's sort of, what I'm trying to do is kind of shatter the impression that this is somehow out of your reach. Now, as far as the design workflow is concerned, there's a sort of conceptualization phase. Then we go into the schematic and we draw the schematic. We do what we call schematic capture, which is capturing the idea in terms that can then be acted on in the physical space. We do what's called PCB layout, PCB standing for printed circuit board. And then we do the computer-aided manufacturing process, which there is CAM in the PCB environment. It just happens to do with 2D planar surfaces as opposed to dealing with three-dimensional surfaces. You can use a CNC machine to remove copper from a pre-clad circuit board in the same way that you can use a chemical etchant to do it. The difficulty tends to be around, or the trade-off tends to be around tolerances and time. I can mill a machine on my desktop, and I can get the board back in a couple of hours. Or I can send it off to a manufacturer. Now, the desktop is going to have a finite resolution. It's going to have some real limitations. But photolithography is pretty accurate, and the chemical process is pretty well understood. So I can go down to 2 mil tracks or 2 mil connections between things. That's very, very small. But on the surface of a circuit board that I send off to a fabricator, but I could never probably pull that off with any level of reliability using a desktop milling machine. Okay? We can get down to about 6 or 7 mil tracks, typically do that with something like an engraving bit or an engraving end mill, something where you really have to then control the depth because it's more depth than anything else, which is going to determine the distance between those things and their thickness. So there's all manner of different modeling and different ways to approach things, but this is an open source software called Fritzing where you can do some basic circuit design in Fritzing. We've got another program now which runs on the Tinkercad website, which allows you to do circuit design and simulation in the Tinkercad context. It's pretty amazing. The reason I like this picture is because, and so there's reference to Homer Simpson there. So there's an episode of The Simpsons, and I apologize if that's sort of old hat now, but there's an episode of The Simpsons where Homer buys a grill. And you see this amazing picture of this grill. It's like this brick grill that he's going to make, out in the backyard and whatever. And as the camera cuts away, it's actually him looking at the picture of the grill on the back of the box. And then he falls to his knees, and that's the grill that he built, right? So beautiful, orthogonal, clean. Again, what's sitting on my desk right now. Hovering, hanging above wires, dangling things, all sorts of stuff. I could be put out by it. I could be frustrated by it, whatever. At the end of the day, you learn to develop a sense of humor. It's like these days, nobody cares when they walk by a room full of software engineers and everybody's got Stack Exchange open. You have to sort of abandon the idea that you are somehow required to know everything. There's a great quip by a writer that I like, a guy named Kevin Morris. And Kevin says, engineers are in constant fear of being found out. And it's absolutely true. Oh my gosh, somebody's going to ask me something and I don't know how to do it. Dare they find out that I don't know something? So let's go ahead and level set. What is a PCB? And again, I mentioned pre-clad circuit board. This is an example of a pre-clad piece of circuit board. You can produce circuit boards on a milling machine. On the right-hand side is actually one of my benchtop milling machines, which is an other mill, now Bantam Tools. And that's an actual circuit board which is milled out on that machine. This board over here was actually done on a milling machine as well. Now there's processes to make circuit boards at home and things like that, but you can see even some of the tolerancing issues that you run into. As you start to get into areas over here where the mill has actually over-milled some stuff. Now, if current carrying capacity is a big deal, because conductors can only carry a certain amount of current, if current carrying capacity is a big deal, then this is one of those areas where over milling like that can really reduce how much current you can actually carry on a circuit board. So that being said, we're going to go ahead and jump into the software, but before we do that, I want to kind of highlight just some really basic PCB terminology, which I think will be useful in trying to understand some of the things that I'm going to reference. First of all, let me jump ahead one here. So on a circuit board, we place components, typically from a library. Okay, so all ECAD software uses a library. Again, we buy 100% of the parts that we use. We place those components down into a design. In the schematic, we have what's called a pin. That's the entry point or the connection point for some signal in the design. In the circuit board, we can call that a pin. Sometimes we do. We certainly do in the context of the actual part itself. However, on the board itself, we've got sort of an interesting trade-off that has to happen there. The board is purely a layer of copper foil. Certain material is being removed. The part that you buy has to be soldered to that. And so the thing that I want to point out here, I'll grab my laser pointer just to enable this a little bit better. Oh, thanks. So the thing that I want to point out here is that the copper foil on the board is actually larger than the geometry of the pin of a circuit board part or a circuit board component. And the reason is that there has to be a certain amount of solder that can accumulate to hold the pin in place. So we build a solder fillet, right? It's a liquefying process. So we're going to liquefy and make molten solder. That molten solder is going to wick up on the tip of the pin. And anytime that you look at a circuit board mounted, or a component mounted on a circuit board, you'll see these sort of large concave kind of sweeps of copper, or of solder, usually silver, actually holding the pins in place. So that connection between components, which is made along that path of that copper foil, is actually the interplay between the pin of the part itself and what we call the pad, sometimes called a land, which is the landing area for where those pins make contact with the board. Okay? Now, we can make contact through on the board in a couple of ways. We can do that in a surface mount way, where a pin has, or where a part has pins which are bent and make contact with the board along the surface on one side of the board, or we can have through-hole pins. And through-hole pins, basically what we do is we drill the holes, then we plate them, then you stick the pin in, and we can solder it from the bottom side of the board. You'll see this with a lot of older electronics particularly. You'll also see this with things that need real good mechanical stability that will actually put holes through the board and allow the pins to travel through the board, so that way those components don't shift around too much. You'll notice this with tabs that hold USB connectors in place, things like that, especially on boards where you're going to plug something in and pull it out a whole bunch, audio connectors and those sorts of things. We'll see some of that actually later on today. So we've got a signal path, we call it a track in the circuit board. That's just the connection between one point and another is made using that layer of copper foil. And then connections between layers we typically call a via. And it's just a way of going down through some area of the board and coming out on the opposite side. So one of the big contributions to the miniaturization of electronics and the availability for us to have things like a laser pointer that fits in something like this was the introduction of surface mount technology, which are components that can sit on one side of the board without any obstructions on the bottom side. And that was largely because now I can put a component in exactly the same spot on the opposite side of the board without the pins poking through, which would prevent me from doing that. When that happened, we got twice the surface area almost overnight. Now over time, the process technology has gotten better, so the size of the tracks that connect things together has gone down, the voltages have gone down, and the currents necessary have gone down, so the current carrying capacity, which is proportionate to the cross-sectional area of the conductor. You know, you wouldn't use, the power cables for a lamp to try to jump a car, because 600 cold cranking amps is pretty significant to try to put through a lamp cord. So because our process technology has gotten better, because we've moved to surface mount technology, circuit boards have gotten smaller, so now you have a mobile phone. And so now you have a laser pointer which fits into something like this, or you've got a key fob which can turn things on and off and enable your car doors and those sorts of things. So as we move through things today, what we're going to do is go ahead and place some components into a schematic. We're going to wire them together in schematic, or create the connections, describe the connections. We'll create a circuit board file, and then we'll go ahead and connect the components together in the circuit board file. So we're going to basically take this process step by step through the workflow. So that being said, enough of the hand-wavy stuff. Let's go ahead and actually get into the software. You should have Eagle installed and probably open on your computer. If you don't already have it open on your computer, then my suggestion would be go ahead and open it. You'll find it in the C directory under Windows, which is 8.4. It'll be called C Eagle 8.4.0, something like that. Let me go ahead and jump in here. When you first open up Eagle, you'll end up with this, and let me hide the 3D stuff in the background because it's just too much of a shiny object. You'll end up with the control panel. And the control panel is basically just foundational document handling, library handling, what's installed, what do I have access to, what am I placing, what am I not placing, et cetera, et cetera. So inside of the control panel here, you've got a couple of different categories. You've got a projects category. And in the book, which you have available to you right now, you have a project which is in there. So went my backpack. You have a project which is in there for an audio amplifier. It's a relatively simple audio amplifier, but I would encourage you downstairs later today, go and check out the factory, because we just took people through another workshop actually showing them how to design the schematic, create the printed circuit board, and right now they're learning how to actually mill out the enclosure and laser cut the actual face of it. But it's a speaker that you can plug an iPhone into, and it works as a fully functioning speaker. Taking that process end to end, which has been really fun and exciting to do. So what you have in that book is an audio amplifier circuit, which taking the relatively small signal, which is coming out of something like an iPhone or a Samsung phone or something like that, and amplifying that so we can drive a speaker with it, because the speaker is a relatively large load as compared to the source. Okay? So in this case, what I'd like you to do is from this control panel here, over the projects, navigate down to where it says Eagle here. Right-click on the project, or right-click on Eagle and select New Project. And then in there, we're going to call this Workshop. It's going to prompt you for a name. You're going to call it Workshop. Okay? Now the project, you should see, again, under Projects, Eagle as a subdirectory. We're going to right-click on Eagle, say New Project. It's going to prompt you to type in a name. I'm going to call it Workshop. You'll notice that you get a little green radio button just to the right of the name Workshop there. All that means is that's the currently active project in Eagle. Okay? Now to that, I'm going to right-click over Workshop, and I'm going to say I want to add a new schematic. We'll do the board later. Don't worry about the board. We're going to do the schematic first. So in the typical workflow, if you remember earlier, I showed just a very simple stack. We've got this sort of conceptualization process, which is, hey, what do I want to build? The next step in that process is to take those ideas and translate them down into a piece of software. And in this case, that involves schematic capture. That involves drawing a schematic. So this is a blank schematic canvas that we can work in. Schematics can be one or more sheets in size. We can have a schematic which has 250 sheets in it if we really wanted to. The truth is that for most small, kitschy desktop type of stuff, I never use more than one sheet. Now there are some designs where I use lots of sheets, but they tend to be pretty sophisticated, fairly robust designs, and the kind of thing that I would do professionally rather than just hanging around the house. Though that's not totally true. If you look at my GitHub repository, which I'll share the slides after this, you'll see a ton of my open source stuff, and it's, yeah, there's a whole mess of multi-sheet schematic stuff in there. So maybe none of that is true, and we should just move forward. So what we want to do is place parts in the schematic and connect them together in interesting ways. Okay, that's it. So what we're going to do is we need, first of all, a library of parts to work off of. And the library of parts that we're going to work off of is available already with mechanical models in it, a whole variety of other things. You have a library menu at the top of your screen. I think it's getting clipped a little bit up there, but if you go to library and then you go to open library manager, you should see a whole series of different Eagle libraries available to you. Sorry, I'm going to remove this one just so I can follow along with you guys, play along at home. You should see a whole series of different Eagle libraries available to you. So what's contained in the Eagle library? And the Eagle library is the schematic version of the part, which is symbolic, the printed circuit board version of the part, which is physical, and then because we've integrated now Eagle and Fusion 360, there's also a mechanical version of the part which includes its full three-dimensional geometry. And so what that means is I can take a design from schematic into printed circuit board, fabricate the board, but I can also take the board into Fusion, and I can then build an enclosure around it. I can apply constraints to a sketch. I can then go ahead and constrain the sketch according to the enclosure if I wanted to. When I move the mounting hole, I want the mounting hole to move in Eagle. We can do those sorts of things. If I wanted to constrain it with a light pipe that's attached to an LED, or if I wanted to add a thermal characteristic to a part and see what the temperature rise is and do some transient temperature simulation or something like that, we can do all of those sorts of things with the integration between Eagle and Fusion. And that's a bidirectional integration. We can go in both directions. Okay. So here I've got a list of libraries that are currently in use, meaning that they're already installed on my computer. Then I have a list of libraries to the right, which are available libraries. Now, the manufacturers of parts, Texas Instruments, Microchip, Maxim, so a whole variety of different parts manufacturers. The manufacturers of parts will provide a data sheet that has typically the representation for schematic. Somewhere on the last page will be the physical representation, which is for the circuit board. And then sometimes mechanical geometry as well. Some of those libraries are downloadable, some of them a little less easy to get your hands on, and so you'll end up having to create libraries. Eagle, thankfully, has a massive community with lots of people eager to teach you how to use Eagle. So you can find all manner of different tutorials on the Autodesk website on how to build library parts in Eagle, how to add new components, these sorts of things. But we also have built a pipeline through this system we call the Library Manager, or the Managed Library System, that allows those third-party contributors to contribute content independent of our release cycle. So if Texas Instruments says, hey, we've got a new library of parts and we want to put it in Eagle, great, do it, no problem. We can consume that and you can use that. So in this case, the library that we're looking for is under the Available tab there, and we're looking for something called Audio Amplifier. Now I've got two in my list, ignore that. That's just because I have one cached locally. I can probably delete that one. But once I select it, I'm going to choose the option to use, and now it'll shift over to the in-use side. That library, because this is a little bit of a contrived scenario, right? Room full of people all building the same audio amplifier. That library is already set up with schematic symbol, printed circuit board footprint, and mechanical model. Otherwise, we would spend a couple of hours building library parts and trying to get those things moving. So more important that we focus on schematic and PCB. So I'm going to go ahead, and once that thing is in use, and if it's in use, it should show up in the list here. I can see audio amplifier now under in use here. I'm going to close that. I'm going to kind of expand my schematic here. And then we're going to go ahead and start placing parts. Now, I think it's about page 5, 6 or 7 inside of the manual that you have there. Maybe it's, so yeah, sorry. 8 and 9. Pages 8 and 9. Talks about adding components to the design. Now, there's a list of components which are on page 9, kind of bottom section there. First, I want to talk just kind of foundational Eagle stuff. Okay, couple of things about Eagle. Let me grab the mouse here for a second, just so I can play along at home with you guys. A couple of things about Eagle. First of all, it is highly modal. Its behavior is very modal. So what does that mean? What that means is typically in Eagle you select a command before you do the before you select the object. Oop. Sorry, that oh, my HDMI just fell out. Sort of anticlimactic there. Plugging in a mouse and I pull out my video. So Eagle is very modal. You select a command before you select the object. So you say, hey, I want to add a part to the design, and then we'll present you with a list of parts. Then you can go ahead and place those components. Okay? If I want to move something, I would select the move command first, and then I would select the object. It's going to feel a little backwards for a while. Eventually, you'll understand why it's that way, and you'll say, okay, yeah, there's a lot of scenarios where this makes sense. There are some scenarios where it makes less sense, and it can be a little bit confusing, and your brain is kind of not wrapped up for that, but that's okay. So you've got an option here, like it says in the manual, to click the Add button. It's just southeast of the trash can. So I'm going to click the Add button, and that should open up a dialog which shows me all of the libraries which are currently installed. In there, I've got a library called Audio Amplifier Example. You're going to have to scroll up and down the list. But once you find that library in the list, you should be able to cycle through the various components in that library by just expanding the library here. And you'll see the schematic symbol, the circuit board footprint, or the circuit board package, which is the area that the part mounts to on the board. So that's where the contacts are on the board. And then the 3D model that's associated with that part. We can visualize all of those. If we get far enough today, we can visualize all of those in a way in which we can see them in Fusion. So we're going to move fairly quickly through the schematic side of things. I'm going to help you to kind of understand procedurally how the things are done. Then we're going to move into the PCB, and then I'm going to show you how to export a design so you can visualize it in 3D, and so you can interact with it in the mechanical tools as well. We will not accomplish everything that's currently in the book today. Okay? We have a relatively narrow span of time, but that's why we printed the manuals. We wanted you guys to have something that you could take with you, and you could go through the process of completing the things that are in there as you choose. So I'm going to go ahead and grab this first part, which is a 90814. If you look on page 9, there's a list of components on the bottom of the page in bold. Next to that, it tells you how many of those parts you need in the design. I'm going to grab that part, and I'm going to go ahead and click OK and just bring it out into the workspace over here. Now, if you right mouse, the part will rotate around the cursor. If you left mouse, it's going to set it down. Don't worry, I can fix almost anything which is broken on anything which you do before I get there. You'll also notice that along the top, you've got a series of different options for mirroring and rotation. So if I decided that I wanted to mirror this part, I could mirror it by selecting one of the commands along the top in that top toolbar. In this case, I'm just going to focus in on getting this part down onto the page. And I want it facing down. You'll understand why in a little bit. Now I'm going to go ahead and hit Escape. And Escape puts me back into the Add dialog. So let me try to talk about this from a workflow standpoint for a second. So the reason why it throws you back into the Add dialog is typically when I sit down and kind of think through a circuit, I'll start drawing things out on a whiteboard or something like that, and I've got a pretty good sense of like, hey, I need this part, and then this part, and then this part, and then this part. And as I get that sort of series of parts together and kind of queued up in my head, then I place a part, I bounce back into the dialog, I grab the next one, I place it, I bounce back into the dialog, I grab the next one, I place it, and I sort of go through that process iteratively until I get all of the components in the design. Rest assured, after we get all the components in the design, we'll start moving things around and connecting them together. What I'd like you to do is just focus first on placing the parts in the design. So I'm going to grab the next component, which we need one of. If you look at the sheet, it says quantity of one. I'm going to grab this, click OK, and again, I'm going to add this to the design. And I'm just going to rotate the part around a little bit, just to show you that it can be done. Now I also need an audio amplifier. So again, I hit escape, puts me back in the add dialog, and I'm just going to run through this list of parts. Next one is the audio amplifier. I need one of those. If I hit escape, next one there is the capacitor. Now the capacitor I need several of. I think I need 5 in total. And how do I know it's a capacitor? Well, I'm an electrical engineer, and I know that 2 plates separated by a dielectric are a capacitor. So that symbol means capacitor to me. Now, it helps that it has the name cap _ ceramic 0805. But truly, that symbol is enough for me to say, hey, that's a capacitor. So I'm going to go ahead and grab that, and instead of just hitting escape after the first one, I'm just going to 1, 2, 3, 4, 5. Place 5 of them one after another. Then I can hit escape and I'll get thrown back into the other dialog. Okay? And so I want to run through that list and get all of those parts down there. You're going to need 2 of the ferrite beads. Don't worry, we're going to look at the circuit in a second and I'll explain a little bit about the circuit as well. So we need 2 of the ferrite beads. I kind of know where they go, so I'm going to sort of like throw a few over on this side somewhere. Go ahead and hit escape. Now, you'll notice that there's a subcategory here for LED, and there are 3 different types of LED listed in that category. I'm picking the 0603 or 0603. Those trailing numbers for LEDs or resistors or capacitors 0805, 0603, they mean something to me. Corresponds to the geometry of the package. So 0.3 millimeter by 0.8 millimeter or by 0.6 millimeter, something like that. That's truly the geometry of that. Okay. So in this case, we're going to go ahead and I'm going to place that as well. And I need only 1 LED. I'm going to drop it down into my design. I need 1 pin header. Now you're sort of disadvantaged to the extent that I know where the parts need to be placed. I need 1 0603 resistor. Now the confusing thing here, and the reason why I brought up the LED and the sizing thing, is that I changed the name of the part since the manual was printed. So you have 1 resistor which is RUS 0603 and another one which is resistor 0805. They're interchangeable. So RUS 0603, we're going to use one of those, and then RUS R0805 is the same as the other 0805. So you need 1 of the 0603 and 3 of the 0805. Sorry?
In the book, you talk about they have the symbol of the square with the point on the end of it, connector pins and everything.
Yeah, so those are actually labels that we're going to apply to name the connections on the sheet. So that's done, but it's not a component. So it's, we'll get to it. Actually, it should be in there. We talk about adding labels and naming things. It's just not covered probably yet. It's probably maybe not in the picture that you have there, but it will be. It's covered in the text for sure. All right, so I want to talk about kind of the schematic for a second. So bear with me for a second. I'm going to go ahead and open up another version of Eagle. I don't want you guys to worry about this. Now that you've got the components down, go ahead and save your design. So Control S, Command S. Just give it the name Workshop. Bear with me for just a quick second while I cheat a little bit here. So here's another picture of that same design. One that I'd done last night, just getting this all straight in my head. And I just want to talk briefly about what this design actually does. And I want to talk about a couple of things which I think are foundational in just understanding how this thing is working here. So in schematic, we connect things together. We use the term wiring or creating networks of connections, what we call nets. I want to explain what you're looking at. So first of all, this is the USB connector in the circuit board. And that USB connector has a power signal coming in and a connection on it we call VCC. Now, without getting into too much detail about collector current or any of those other sorts of things, this is an incoming voltage from VBus. VBus is a USB signal from the USB standard, which is where power comes in over USB. A USB port by default on your computer or a USB signal by default can handle or provide 500 milliamps of current, unless it's coming from something like a charger which can handle more. USB-C ramps that up, which is intended to make it easier to do fast charging of stuff and try to build things which charge a little bit faster or will allow you to do things like laptop charging over a USB connection, which is what obviously Apple has done now with the newest version of Macs. I have ground here as well. GND is just short for ground. If you think about a battery's got two leads on it. It's got a positive lead and it's got a negative lead. The positive lead and the negative lead, if I connect a loop through them, they short out. Okay? When they short out, it heats up really fast, and all the power is kind of drained out of it. When I connect in between power and ground, a series of circuitry, it functions as a load and controls how much power is actually being routed through that particular connection. Okay? So what we're doing here is basically creating a closed loop between that voltage and ground. Okay? Now, it kind of doesn't look like that because this isn't connected to this, isn't connected to this, isn't connected to this explicitly. We haven't drawn a loop. You have to understand that most schematic capture tools or ECAD tools, we've just done that so you wouldn't have a bunch of wires all crossing over each other and trying to figure out then how to read that design. So as an electrical engineer, I know VCC connected here is the same as VCC connected here. There is a virtual connection in between these things that I don't really have to think about. As long as I know that's VCC and that's VCC, those two things are connected together. Just as this, which is ground, is connected to this, which is ground, which is connected to this, which is ground, and this, and this, and this, and this. So those things are all connected to each other. Everything in here needs a source and a return. If there's a break between the source and the return, we have an open circuit and it doesn't work. Okay? Now, how we control when power moves between source and return and things like that is how we do things in interesting ways. Okay? But every time that an output, in this case this is an output, every time that an output goes high somewhere, the power system has to respond to the needs of the circuit. Okay? We switch things on and off all the time. Those things are changing with relative frequency. But the circuit has to respond to provide instantaneous power, near instantaneous power, anytime that we want to do something. So in this case, this is a relatively simple circuit. We've got the USB connection, which is providing power. The two data lines, D- and D+ for USB, aren't being used. So we're just using USB just for power. Now over here, we've got an audio connection. This is your standard sort of stereo audio jack. Okay? And what's coming in over that audio connection is something we call AIN+. And what that is that's the positive audio signal or the combination of the two audio signals which are coming in over that stereo audio jack. Now what we're doing with that is we take that and we put that into this thing over here. This is a connector that allows us to connect a potentiometer, a knob to it, which allows me to control the volume. And all that is a variable resistor. That then feeds into an amplifier over here, and the amplifier will go ahead and amplify that and drive stereo outputs over here, VO plus, VO minus. That's my output positive, my output negative. When you plug in stereo cables, you've got the black one and the red one. That's your positive and your negative, or your negative and positive, if I keep my ordering right there. On the front end of this amplifier, there's a filter. That capacitor in there filters unwanted frequencies. What does that mean? Well, your ear can hear things in the range of about 15 hertz, which is pretty low, up to about 22 kilohertz. Okay? Anything beyond that, sort of outside of the range of how your ear operates. There are all sorts of what we call harmonics, these other frequencies that start to appear just as a function of electronics happening. And I'm trying to simplify this as much as possible, but what we're doing with the capacitor is allowing, or with this here, is allowing a certain amount or a certain frequency range to come in and block other frequencies which aren't relevant to this particular design. If I want to drive a speaker, I don't want every other frequency which is kind of not relevant in the normal audible range to come in. I don't know if any of you ever had a lousy USB charger and you can hear the ultrasonic sound coming off of it, super high-pitched squeal coming off of it. You get these strange frequencies that start to show up, that you can hear sounds being made by electronics that are ambient electronics. There's no motion there. There's not even a speaker there, okay? It's just the radiating electromagnetic frequencies that end up in some sort of an audible range. So in this case, we've got a little filter on the front end of this, and then we've got some filtering on the back end of this to make sure that we filter things out before they hit the speaker itself. So what I'd like to do is, following this as a guide, let me explain, first of all, I'm going to go back to my design for a second here and kind of explain just briefly some of the wiring concepts in here. There's a little green hockey stick down here, which if you hover over it should say net. Now, for those of you that are AutoCAD fans, myself included, Eagle has an active command line all the time. So if you don't like going down to the toolbar and finding things in the toolbar because the iconography maybe isn't as conducive, or you just think it's that much cooler to do things using a command line, you can just type the word net and hit enter, or I can click on this icon over here. Either way, I achieve basically the same thing. But this is the wiring tool that we would use to wire things together. I'm just going to demonstrate it. I don't want you to use it yet because we're going to move some components around first. But the wiring tool, you'll notice that when I hover over the top of a pin, the wiring tool becomes active, and as I hover over another one, it shows me, hey, those two things are electrically connected. I can click to anchor points along the way, and it will demonstrate that those things are electrically active, okay, or that they're electrically connected. So what we're going to do is move the components around in the design to reflect something which looks somewhat like this. Now, there are a few symbols that you don't yet have in the design. You don't have the VCC symbols or the ground symbols yet. My suggestion is wait until you get the other stuff wired together, and then let's go through that process of adding VCC and ground. So let's go ahead and let me just, for the sake of helping to kind of move forward here, we're going to Let me move this. Now, if I want to move a part, let's say I already placed it. If I select the move command, which is this four-way arrow here just south of the crazy eyeball looking at me, this command here, if I move it and I click on the part will have a hotspot for where I can pick it up. If I don't click on that hotspot, I can't pick up the part. Okay? I have to click on the hotspot to pick it up, and then all the other stuff that was available to me before, like the ability to mirror something, the ability to rotate using the right mouse button, those things are all available to me. Okay? So what I'm going to do here is I'm going to place this part over here. I'm going to go ahead and grab my resistor here, grab another resistor here, grab another resistor, drop it here. I'm not so worried about perfection at this point. I'm more worried about just getting the parts where they can be easily connected together. I'm sort of focusing in on this side over here. I happen to know this side over here already. But you should have in your book an image which looks very similar. The key difference in your book is that I used these squiggly line resistors for the left-hand side of that amplifier. And the reason I did that is because I don't like those rectangular resistors. There's arguments on both sides of that. It's probably the last holdover from World War II. The Europeans use the rectangle for resistors because they say that our squiggly American resistors could be confused for inductors, which have little hooks. And we Americans say, but that doesn't look like a resistor, it just looks like a rectangle and I don't know what it does. So we use the squiggly line. It's this last grand debate between the Europeans and the Americans. So I'm going to get most of these components kind of lined up where I think they need to go. And I'm using that other schematic as an example here because I think I gave away my manual. So that's why I have this fully baked schematic over here, very Julia Child style. For the younger demographic in the room, that was somebody who was very famous for pulling cakes out of the oven fully baked on a cooking show. So the LED hotspot is right here at the intersection of these two things. This is something which, as we move forward with Eagle, we'll end up improving a lot of that behavior because there are a number of things, a number of subtle things like that that I think we could probably do a better job with. Sorry, to which one? Oh, this here? Oh, this one. Ah, this one. It's right over PS1, or $1. No, it's okay. It's okay. I used to complain that people, their vision, it's just not so good. I don't know why people have such a hard time seeing. And now that I'm in my mid-40s, I hold my phone at arm's length, text people. Pretty soon I'll be calling my 18-year-old and asking him to come home and fix my computer. Yeah.
So I saw one in the past teach other people, but very basic using Autodesk as migration of circuits into Tinkercad. Is this whole hotspot thing the reason why it's also very challenging?
No, so circuit design in Tinkercad is very different. So that's all breadboard based.
Well, I mean, when you're dragging the actual objects.
Oh, you're talking about in the circuit editor in Tinkercad? Show me afterwards. I'd like to see exactly what you see and how it behaves. just so I kind of understand it. Tinkercad shouldn't have the same hotspot problem, but if it does demonstrate that problem, it's relatively easy for us to fix, and I would prefer feedback from people so I can help enable that process. So in this case, I'm going to use now, I've gotten most of my components in place. I'm going to use this opportunity to go ahead and place the two other symbols which are in my schematic, and I'll show you the schematic again up here, which are the position of my ground and VCC symbols. Ignore these little labels over here for right now, just get these things in place. So those are actually components. Eagle uses components, parts, so I would go to the Add menu, and under that same library that we were pulling parts from before, I'm going to grab VCC from that Add menu, and let me go back into the design that needs them. So I'll go to the Add menu, I'll grab VCC, I'm going to click OK. I'm going to go ahead and drop a VCC connection here. I think I know I need a VCC connection here. I know I need a VCC connection somewhere in here. And I'm going to put that there. Then I'm going to go and hit Escape, and I'm going to grab ground. So this is kind of what I'm going after here.
So I tried to put this VCC in and it's not giving me.
Let me swing around and take a quick peek here. Yep, so just, let's see. So you're in the replace command instead of the add command. Oh, so okay. You want to go to replace, or you want to go to add.
Okay.
Oh, hang on. VCC, yeah, there you go. So now you've got that there. Now, then you can just go through and, yeah. Yeah, so if you use the move command, after you've placed some stuff around, if you wanted to flip the USB and kind of move the USB around, if I use the move command, and I can right-click it and choose move, or I can click the command over here and choose move. To get the USB with the pin pointing down, I'm going to click this mirror option here. So it's mirrored this way. And if it's mirrored using this mirror option, this last mirrored option in the list, then when you rotate it, you'll eventually end up with the pin facing down. So once I've got most of the components in place, and because I want to kind of accelerate the velocity of what we're doing a little bit, I want to show you using the net tool to connect some things together. Okay? So again, grabbing my little green hockey stick here, which is my net tool, that's the network tool. That's going to allow me to create a network of connections between stuff. I'm going to go ahead and start making connections into things. And again, when I click over the pin of an object, I should get a little green circle. That little green circle shows me that those two things are connected. Now, because Eagle is modal, I'll stay in that mode. until I hit escape and break from that mode. What I'm trying to do here is essentially connect a series of things together in interesting ways. So if I get my parts placed correctly first, then wiring becomes almost a no-brainer. Now there are some things for which you don't have answers yet, and I'll explain in a second what they are. Those small little labels that you see on the end of a wire. And again, we're going to do part of the circuit. We're not going to do the whole circuit, but let me just explain what those last things are that you see that kind of don't make a ton of sense right now. So right now, every one of these wires, every one of these connections, we use the term wire and net interchangeably, but every one of these connections has a name, whether you know it or not. If I right-click over a wire and I say name, it shows me the name. And in this case, the name of this is N$11, something like that. It's just a system-generated name. And the system generates names to keep the names of these things independent. If I don't explicitly name it, the system will give it a name. It'll say, hey, I've got to call it something. And to prevent a short circuit between this thing over here and this thing over here, I'm going to give them separate names. If ever I try to connect two things with the same or with different names together, the system will say, you've got to tell me what are we going to call it. Because otherwise, it's sort of a cardinal sin. At that point, you've short-circuited two things together, which could be very, very different things. So the software looks for total clarity in terms of how the names are applied to objects. Okay? That holds true for components. It holds true for nets. And so when I decide that I want to name something, I can right-click over a wire and I can say, hey, I want to name this. If I go back to my original reference schematic, this first wire over here was named VO+, and this is VO-. If I go back to my other design, if I right-click on this and I give it a name, I say, hey, I want to call this VO+. This one below it, I want to call this VO-. Right-clicking on those wires, I can use the name tool, and that puts me in the naming mode. Okay? If I click on one of these wires which is adjacent to VCC, and I say, hey, show me the name of that thing, it tells me that the name is VCC. And the reason is that this is a special type of symbol in the schematic tool, special type of component that says this is where the power is coming in. Okay? Now I have the same would be true for ground. If I click on a wire using the name command, which is this command over here, you could also just type in name in the command line and hit enter. Or you can right-click on a wire. If I right-click on a wire which has one of those ground symbols attached to it and I say name, it says, hey, the name of that thing is ground. Do you want to change that name? And if I do change that name, I get a choice. Do I want to change it for that segment, or do I want to change it for the whole connection? My advice to you is for anything which is VCC or ground or 5 volts, anything which is power, whether it's the return or it's the source, don't change the names if you're using symbols like that, because it'll be misleading. Yeah. You can definitely have +5, +12, +3.3, all of those things. And there's symbols for all of those in the Eagle library. However, if you have something called VCC and you put a symbol on there called VCC, don't rename the wire VN because the symbol says VCC. And you're going to go all over the place, go batty trying to find where VN is. And you realize that you named a wire something, but the symbol, because it's a library component, and the library component can only be changed in the library, it's going to be out of sorts, and those two things aren't going to look like they're consistent with each other. So in this case, if I decide that I've named, for example, VO plus and VO minus over here, I can then go ahead and right-click on it and choose to apply a label. And that label shows, hey, I'm attached to this wire, and the name of this wire is blah, 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 right? In this case, VO plus. Now, the label has a couple of different types. There's one which looks like this, and there's one which looks just like a piece of text which would be attached to the wire. They do the exact same thing. One just looks slightly different than the other, okay? So I can say, hey, I want this to look like VO plus, and I want this thing to be VO minus, and I can add the label by simply right-clicking on the wire and saying, hey, I want to label it. Now, if I label something in which I haven't named it already, then the label that shows up is going to be something that the system generated, which may not be terribly conducive to understanding where it is. $9 kind of doesn't mean anything to me. It's just a way for the system to disambiguate. It's not really anything like, hey, this is data 0, data 1, $9, kind of not terribly helpful. Yeah?
That second line down, I mean, you got the documents file and all that. My screen didn't have the second line down.
Oh. Then maybe you're not yet in the label mode. So that second line down in the toolbar right here only shows up when you're in a command. So if you're not in the label command, then that second line down wouldn't show up. Yeah. Yeah, so you can set hotkeys for everything in Eagle. We don't out of the box because we have the command line. But if you go to options and then set, I think there's a tab for hotkeys. You can create any kind of hotkeys that you want, and then you can reuse those hotkeys from computer to computer if you wanted. Oh, maybe it's options assigned, sorry. And you can actually, Eagle's got a really powerful scripting system in it. It's also got a system of commands where you can chain multiple commands together. So you could say, hey, I want to build a hotkey which places a rectangle that has this geometry. And you can chain any series of commands to any hotkey that you wanted to create. So you're absolutely thinking in line with what's coming. This is being recorded. I won't say too much. Let's talk after class. All right. Yep. All right. So let's go ahead. We've gotten the components down in the schematic. I want to just take you over to the printed circuit board editor and show you the difference between these two. Anytime that you create a schematic, if you start with the schematic, there's a button along the top up here, just to the left of these numbers. It says schematic and board, or SCHBRD. It's hard to see, maybe. The high DPI screens these days make everything hard to read, but if you click this little button, it's gray and green. If you click this button which says generate, switch to board, it's going to say, do you want to create a board from the schematic? The answer to that is yes, absolutely. Now, as I said, we're not going to complete the whole schematic today. We're not going to complete the whole board today, but I wanted to at least give you a little bit of food for thought, enough information to kind of get started, and then give you the materials to take with you so you can at least start getting comfortable using the software and building a printed circuit board from it. So this opens up the printed circuit board editor. And the black area in the printed circuit board editor over here, this is the board as it is today. And right now, it is much larger than it needs to be. It's about 4 inches by 6 inches or something like that. Absolutely no way that I would need that size board for this many components. I want to mention a couple of things. The components that were in schematic, that we connected together, when we bring them into the printed circuit board, the software automatically draws small lines that show where they should be connected. It doesn't create the connections for you, right, when it dumps it into the editor, because we don't know where you want to put the parts yet. We do have an auto router, which will create the connections for you, but it draws connection lines, sometimes called a rat's nest. In Eagle, it's called the air wire, which basically shows you, hey, these things need to be connected. Part of the reason why we show you the lines is because we want to show you things like, hey, if I put this part, if I move this part over here, let me just grab this part here. If I move this part and I start rotating it around, I may create a lot of crossovers, I may create a big jumble of a mess, but maybe in the case of a part like this, if I move this part, rotating it in some direction will reduce the number of crossovers and make it easier for me to create connections between the parts. Okay? Before we start moving parts around, I'm going to go ahead and resize the board. And to do that, I'm just going to click and hold. So I'm going to go into the move command. I'm going to click and hold, and I'm going to drag the outline, the default outline, over here, and then drag it down. And now I'm eyeballing it because this is a workshop and it's highly contrived. Okay? But if you had created a sketch in Fusion and created a board from that, you could bring that into Eagle and say, I want my mechanical design to drive the board shape. Absolutely, totally okay to do. On the far right-hand side, there's a button that says Fusion Sync. That Fusion Sync button would be if I wanted to bring a board shape in from Fusion, or if I wanted to push my design into Fusion. We'll talk about that in a second. What I like to do now is just kind of get some of the components on the board. So I'm going to drag the board out to be a reasonable enough area that I can do this easily. And just clicking and holding the parts by their reference point will allow you to drag the parts on the board. Now, I've got a few parts here, which I just happen to know because I'm part of the team that built the design, are connectors. So this is the audio jack. You can imagine that the audio connection is going to come in over here. This is the USB jack. You can kind of see the little flare on the edges of the USB jack there. So I'm going to move these parts sort of off to the edge over here. And then I'm going to start moving the rest of the parts onto the board. Now, this is going to be a fairly inexact science right now, simply because we have a limited amount of time to do this. So I'm just going to get the parts onto the board. Now, I'll be finicky with my connectors over here and make sure that the two connectors that I have, which are, again, this audio jack and this USB jack, both of those are off to the edge over here. Then I'm just going to get the rest of the parts onto the board. I'm not really going to worry about it too much right now, because I want to show you how to actually build a mechanical version of this design. But I also want to mention to you how ways in which you can connect things together on the board. And there is a set of instructions on how to create connections between things, physical connections, by routing connections on the PCB. And routing connections is just the process of you forming those physical connections between objects in copper. So if you think about it like generating the paths that are necessary for electrons to travel to do some work on the circuit board. So I just dragged a bunch of stuff into the board. Don't worry about it too much. I dragged the board, resized the board, And I dragged a bunch of parts into the board. Got one still outstanding. Sorry, I thought I moved that already. Drop it over here. All of my components are on the board. Rule number one, if I go to produce my board using the make button at the top, I want my components to be on the board and not off the board. That would be pretty catastrophic. So once I've done this, let me show you just the basics of routing the board together. So there are two tools here. There's a tool for routing and a tool for ripping up connections. The routing tool is what I would use to create connections between components, and I would use these air wires to guide me in that routing process. So if I choose the route tool here, and I click on a connection here, a pad, I can create a physical connection on the board. Now that would actually be done in copper. The width is defined here. So if you imagine that I said, hey, I want to change the width of that to, I don't know, 15. That'll get wider. Right now, the units are described over here, in this case in mils. So that's 15 mils wide. Okay? And I can create then physical connections following those guide wires or those air wires into the components in the design. Now, the software is smart enough to prevent you from taking a connection which is different, or a net which is different, in this case net $10, and shorting it with VO minus. That would be catastrophic. Okay? The best outcome is it doesn't work. The worst outcome is it catches fire, burns down your house, and you have a pretty horrible thing to explain to whomever. So now circuit boards, because they're multi-layer, I can create connections which span through the board. We do that again by drilling a hole and plating it. And it's just the space bar that you press to create a hole in the board to allow you to change to the opposite side of the board. Okay? Now, because we don't have a ton of time today and we're not going to be able to complete everything today, the manual talks about routing. There's also a command called an auto router. What the auto router does is it uses a series of fairly sophisticated topological algorithms to determine how to connect things together based on the rules that you give it. So in this case, the auto router is saying, hey, do you want a preferred direction on the left-hand side? And what that really corresponds to is which way should the tracks tend to go on the top versus the bottom. If I had multiple layers, on the next layer I could say, hey, I want it to go this direction or that direction. Part of the reason why we change directions is because if you go back to the original concept of a capacitor, well, it's two metal plates separated by a dielectric. If on the bottom side of the board I have a large area of copper, which is directly adjacent for a long period of time to copper on the top side of the board, a capacitance forms in between those because the PCB itself is an insulator. Two metal plates separated by an insulator. We call that parasitic capacitance. It's capacitance that forms that you didn't know was going to form. So I'm a radio guy, and as a radio guy, we think about parasitic capacitance all the time. Because radios, if anybody goes back to old trench radios from the war, or you go back to any of the sort of old condenser-based radios, condenser was a word for capacitor before we called it capacitor. The capacitance and the inductance, which is determined by the coil of wire, determine the tuning of the radio. And if we start adding additional capacitance here and there that we don't keep track of, we can whack things to different areas and not get the right signal, or the signal strength will be less or more. Just, try to tune an FM radio sometime as you're driving down the road. Like, just, don't pipe just purely digital music in it, but actually listen to the radio. Not many people do, I don't think, anymore. Anyway, so we can change routing biases, or we can tell the router to do it for us. In this case, I'm going to set the effort to high, and I'm just going to auto route this. And I'm going to tell the auto router to go ahead and route my board for me and see what it does. And in, well, far less time than I would, the auto router has routed the board, completed the board, and used 5 vias to complete all of the connections on the board. Now that's faster than me. There are limitations in terms of the auto router, okay? If I've got really complex designs, really complex set of constraints, where the physics are going to really drive the behavior of the board, auto routers don't work, okay? But auto routers are great for determining whether or not the placement is good enough for you to manually route something, and then also great for designs in which it's, hey, as long as they're connected, it's not a big deal, okay? So I'm going to go ahead and save the design. And then what I want to do is I'm just going to show you the last mile here, because we're running short on time, is the synchronization of this design over to Fusion. So if I click on Fusion Sync over here, I have a choice to link this existing design to link this to an existing Fusion design, or create a new Fusion design from my existing board. I'm going to choose to create a new one, click Next, and then in the subsequent window, I'm going to choose Demo Project, which is a directory that I know all of you have, and click OK. What this shows me is a list of all of the components in my design. It says, hey, all of my parts, they have 3D packages attached to them. That may not be the case, and that's OK. Some parts I care about. My connectors, where they're going to meet the outer boundary of the case. I need to remove some part of the enclosure so a connector can punch through it. I want a USB jack to come there. I want the slot for the USB jack to be cut out of the front panel of something. So for those, I probably want the 3D component or 3D model attached to it. But for every resistor and capacitor in my design, it's not really a big deal. Okay? For everybody who's interested, there's a 30-minute webinar. If you look up Fusion, Eagle, ECAD, MCAD, ECAD for electronics, MCAD for mechanical. There's a 30-minute webinar / tutorial that I did which shows you the entire pipeline. If I push the design to Fusion, it's going to go ahead and generate a new design. It's going to put it into my demo folder. It's going to give it the same name as what I called it here, which is Workshop. It's going to generate from those 3D models the board outline. It's also going to go ahead and dereference the 3D models from the library and populate those into an assembly in Fusion. So now I'm going to have a project in Fusion which happens to have the board shape, the parts on it, the connectors where the connectors need to be, in this case my routing and connections, which isn't totally relevant on the mechanical side. But just to prove that, that I'm not a liar, we'll go here and I'm going to jump into Demo Project. I'll hit refresh on my demo project. And somewhere in Demo Project. Oh, is it? Oh, yeah, it's alphabetical. Who knew? Thanks, I appreciate that because I've just been doing that all day. It's just on YouTube. It was something that we did as a part of the launch of the ECAD-MCAD integration. So we launched the connection between Eagle and Fusion in August of this year. It's in beta-ish, what we call preview in Fusion. If you want to use the PCB features in Fusion 360, you would go to Fusion 360, then Preferences. And under the preferences, under preview, there's a checkbox for PCB feature. Okay? But this is your board, my board, I guess, in this case, in 3D. Now, the nice thing is I can create a brand new project, say, hey, I want to create a new design. And then into that design, I can draw a sketch. You know, I grab a 2-point rectangle and say, hey, I want something which is going to be, I don't know, yay big. Grab that sketch, finish my sketch, go ahead and extrude this thing if I wanted to, extrude it out a little bit, create an opening in it, whatever I wanted to do with it. I can then go ahead and insert my board into the current design, and that'll add that. Oh, I've got to save my sketch first, sorry. If I insert this now into the current design, that'll add that to my browser into my assembly tree over here. And then I can start building my enclosures around that. I can build sketches off of the board. I can create constraints around it. All of the other stuff that you would do in the mechanical space. Okay? Now you have the ability, because you're using mechanical CAD software, to do things like associate thermal models to components in the design and see what the temperature rise might be and how that might affect an enclosure. Because electronics produce most of the heat, other than motion, produce the heat, which is going to be probably the most parasitic to that nice injection molded plastic enclosure that you just built, right? Or the heat that's going to drive that nice aluminum enclosure to where you don't want to touch it anymore. So we have all of those simulation capabilities inside of Fusion to be able to build enclosures around things. All of that stuff is available. To give you a sense of just, and I'm not a sales guy, I'm a product development guy, but let me end on a high note. Eagle has a free license, as does Fusion. As you level up to a commercial license, Eagle's first tier commercial license, which is for 4-layer circuit boards, which is pretty comprehensive, is $100. Fusion is $300. So for $400, you can have end-to-end electronics and mechanical design. That doesn't exist anywhere. And I mean, this is as a guy who's been in the CAD business for 20 years. It doesn't exist anywhere else in the industry. It's one of the things that I'm super excited about, and one of the reasons why I joined the company was to build this type of integration. And we're continuing to grow and develop that integration. So look for the combination of more and more of this technology as we move forward to try to really build the comprehensive workflow. So that's it. That's that's about as far as we're going to get today. But if you guys are interested, by all means, pull me aside out in the hallway. We can ask and answer whatever questions that you're interested in. You had a quick question before we.
Yeah, after you finish your PCB layout and everything, did you create a software package I can send to a vendor to print their work for?
Yeah, actually, in that toolbar, that main toolbar in the PCB editor is a button that says Make. Okay. Click that button, and it'll produce all of the downstream output files that you need. Okay. And then that will give you the package. It'll also put it into your profile. You can download all of those files and give them to a vendor, or you can just point them to those files. Yeah. Any vendor can read them because they're standard. Yeah. Yeah, so the standard that we use in PCB is very similar to G-code, but just plainer. So, yeah. Anyway.
All right, Matt rattled off a bunch of documentation and videos and whatnot. View them where they are. I have my cards up here. I can email them off to you guys. Just go ahead and just email me my email on the card and just say, hey, I was in that class. Can you please just give me all the documentation that you discussed in there? We have a tremendous amount. The Eagle integration, PCB design, schematics, and there's articles, tutorials, training classes, there's videos to help you throughout this process. You have the book. There's a good step-by-step on there. If you have any questions, I'm available on there. Thank you so much.
Thank you, guys. Take care.